So we can go ahead and get started.
Sure, whenever.
So thank you all for coming. Today I'm excited to introduce Professor Malena Rice. Malena completed her PhD at Yale before working as a 51 Vegas IB postdoc at MIT, and then she returned to Yale as a professor. So Malena is an expert in exoplanetary systems and how they're formed and their dynamical structure, so I'm excited to hear what she has to say. Please feel free to take it away.
Thanks so much. Thank you for the invitation. It's been really nice getting to spend the day here and scope it out prior to coming back in a month for the Division of Dynamical Astronomy conference. So I am going to talk about a range of things that I've been working on over the past 5 years that are kind of broadly encompassing this topic of orbital architectures of planetary systems, largely trying to address a lot of big questions in this field from an observational standpoint and try to put better constraints on our understanding of what processes are dominating the evolution of planetary systems. So I wanted to just start off by shouting out my wonderful research group. So I just started about 8 months ago at Yale, and the group has been pretty dramatically growing. So a lot of the work that I'll be talking about has had contributions from this group here, and I have quite a few incoming undergrads as well. So the group's been really ballooning, which has been pretty exciting. It's a lot of fun to work with so many great students. So the underlying thread of my research is trying to understand what underlying mechanisms are producing the broad diversity of planetary systems. I approach this from a little bit of solar system standpoint as well as out to exoplanets. So I'll be talking about kind of from the more close by solar system heading outwards in terms of the contributions that I've made. And I wanted to just start with this standard exoplanet plot that you'll see a lot, which is just showing where the known exoplanets are as of today in orbital period space versus mass of the planets, as well as where our solar system planets are. So I think it's useful to just revisit this, even though it comes up in lots of talks, but it's continually expanding. So we now have over 5,600 exoplanets that have been confirmed, as well as thousands more, actually more candidates than confirmed planets from the TESS mission, as well as some that have not been confirmed from the Kepler mission. So we're really at a point where we know of enough planets to start really figuring out at a demographic level what is going on in these systems, particularly for some of the better constrained populations within this diagram. So I want to really emphasize that while our solar system is in this kind of sparse region of parameter space, we have not found a lot of exoplanets there. That doesn't mean that solar system-like planets are uncommon. This is just basically a map of detection biases in a lot of ways. And so this region down here is pretty much our incomplete space where we aren't able to tell whether there are exoplanets there, which means that, the universe has been quite kind to us by giving us many non-solar system-like planets to study as we're making our way towards the bottom right of this figure. So what do we know? We've got, if you just look at this, kind of 3 immediate blobs that sort of pop out among the exoplanets that are in gray. So these are the hot Jupiters, which we know of a lot of them. They're actually quite intrinsically rare, but they're the easiest ones to find. So they comprise a pretty large chunk of the exoplanets that we know of. We've got our super Earths and sub-Neptunes. These are quite common. We don't have any of these in the solar system. They're kind of between Neptune and Earth, but it looks like they're pretty prevalent across the sun-like stars in the solar neighborhood. And then around sun-like stars, we also have about 10% of them hosting cold Jupiters. So this is probably the most immediate constraint on, if you want to know whether our solar system is common, and if you think that something like the solar system requires a Jupiter-like planet at a Jupiter-like separation, this already tells you the solar system is not common. So it sort of just depends on how you set your parameters, how you actually want to define what is or is not unusual about our solar system. So a lot of my work has been trying to better understand that. I will be going through this, trying to understand the relationship between the different components of planetary systems. So I like to step back and kind of think about, there are a lot of components besides just the planets themselves. We've got our stars, we've got our planets, and we have our minor planets. And so I worked to try to understand all of these together using a variety of constraints. I'll follow this map through the rest of my talk with a couple of questions that I've been working to address over recent years. So the most nearby that I've really worked on extensively has been trying to understand this question of Planet 9 and if there is a ninth planet in the solar system. So I'll just start with, why would we think that there are more planets in the solar system? So if we take this kind of very simplified image of our solar system and just look beyond our simple schematic, this is showing a map of the minor planets that have been found on quite wide orbits. So you can see Uranus and Neptune are off to the left of the figure to date. And so there are pileups in the classical belt towards some mean motion resonances that are delineated on the top figure here. You can see there is quite a large population of bodies in the bottom left, and then this again is detection bias. So we're seeing semi-major axis versus eccentricity. The objects that we're able to see are the ones that get within some parasector distance of the solar system such that we can see them at their close approach. So not to say there isn't anything out here, but we're able to see the minor planets that kind of follow this eccentricity semi-major axis trend. So if we look at the most distant detached Kuiper belt objects that are really not interacting with Neptune at all, so their entire orbits are beyond the kind of classical picture of the solar system that I showed earlier, there has been the suggestion that if you look at just the long-term stable ones that are these purple orbits here, they appear to be preferentially clustered on one side of the sky. So I want to emphasize that this is heavily contested back and forth in the literature, so this is not something that is strongly agreed upon. It could be a detection bias that we maybe are just better at finding certain kinds of orbits, but this is sort of the claim for why this canonical Planet 9 potentially might be thought to exist if you believe that this is real. So the reason that this is strange and that you can't get this from a stellar flyby or something else is that we should have our orbits in the solar system processed and actually spread out across the sky over about a billion-year time scale. So if something had happened early in the solar system to produce such a perturbation, then you should have seen the orbit spread out by now. Or if you had a stellar flyby more recently, then that's actually a lot less likely to have occurred. So the idea is maybe you could have a Planet 9 instead that is producing kind of a torque on the rest of these orbits and forcing them to stay confined to a particular angular region of space here. So this is just some equations to describe how you would expect the outer giant planets in particular, that's J equals 5 through 8, to force these orbits to actually spread out. And that's how we get this billion-year time scale. So if this Planet 9 existed to reproduce all these orbits, it would be really far away, and that would be why we haven't found it. So this is from the most recent paper that has kind of put more updated constraints on where we think Planet 9 would be. It would be about 6 Earth masses, 380 AU. If you've been following the Planet 9 idea for a while, since 2016 or so, when it started to become more popular, it used to be farther away and more massive, and as more of these distant trans-Neptunian objects have been found, the predictions for where it would be have been moving inwards, and the idea would be that it'd be a little bit less massive, such that we still wouldn't have seen its perturbations on anything in the solar system. So that's sort of good if you're looking for Planet 9 in reflected light, in that despite being smaller, if it's closer, it would actually be brighter. And so that helps if you want to look
So what
for it.
drove their decision to move the semi-major axis, or what observation caused them to think it was closer? Because it's the same two guys that have been pushing it forever.
Yeah. It's the detection of some more of these extreme TNOs. So same models, but just
with a
updating.
bit more spread in the area?
Yes, I think so.
Because if they were all lined up again in the same region, they would have
Yeah.
presumably at once.
Yeah, so it's just a couple of additional observations that I'm not sure how much they actually updated their models as well, but it just keeps getting closer and smaller. Is the punchline that I've taken from that.
Right.
Okay, so If Planet 9 existed, or it doesn't have to be Planet 9, if any planet existed in the outer solar system that we hadn't found, it would have to fall in this region of space here. And it turns out that this Planet 9 would, such that you wouldn't have seen it. So it has to be faint enough, low enough mass that it wouldn't be bright enough that all sky surveys have found it. It'd have to be big enough to be considered a planet. So that's this green line here. It would have to be close enough to not have gone unstable in the sun's birth cluster, and it would have to be far enough that Cassini and Juno and various other orbiters that have very precise positional measurements of the solar system wouldn't have actually been perturbed and seen the signatures gravitationally of such a planet. So there actually remains a pretty large space where you could hide planets. There have been other planets that have been suggested, maybe Mars-sized planets that could be lurking in the outer solar system, and all of them would fall within this rough range of parameter space. So I've been working on looking for just anything that could be hidden that would be pretty bright and very slow moving in the outer solar system with the Transiting Exoplanet Survey Satellite, or TESS. So this is a NASA satellite that's been observing for about 6 years now. It's doing all sky surveys where it stares with its 4 giant cameras at each part of the sky for about 27 days at a time, scans around. This is showing the initial version of the primary mission, which actually ended up being altered a bit because of scattered light. So some of these sectors were moved upwards a bit, but the primary mission, the goal was really to cover a very large swath of the sky, primarily to look for exoplanets around bright stars, but that also gives you a ton of data for the solar system, where you're staring at a particular part of the sky for about a month, and you're gathering quite a lot of photons for any slow-moving objects that might be hidden there. So again, this is just the primary mission, but TESS has continued to observe for about 4 years beyond the primary mission, so it's actually covered in most of the rest of the sky that's not shown here. So I put together a pipeline a couple of years ago that is pretty much just removing everything that's bright in those regions of the sky and saying we're going to ignore the stars, we're going to remove everything that we know of and see what we can pull out from the noise. So it takes all of the systematics and stars out of the system and is just shifting and stacking images along potential outer solar system object paths in order to see what might remain that we could identify just blindly searching through this large data set. So this is just showing a more concrete example of what I mean by that. So on the left here is masking out stars and other bright objects. You can still see some asteroids moving through. These are bright foreground asteroids on the left. And then on the right, we're shifting and stacking images to recover Sedna, this very faint extreme trans-Neptunian object. Its at V is about 20.9 or so. So you can't see it at all in individual images, but as you start stacking hundreds of images, the signal pops up pretty nicely. So that's the general idea of this method. So Sedna, we know where it is, so you can apply this method pretty easily, just saying, okay, we'll remove everything else and pull out this signal. If you don't know where an object is, that's a little trickier. So that was what this proof of concept was doing, where we first of all, just recovered a couple of objects along their known paths and showed that we can go down to V equals 22.3 is the faintest object shown in this example. But then we also, in this middle and right column, just shifted and stacked along all reasonable paths for anything beyond about 70 AU in the solar system. And we were able to blindly recover Sedna really well, but even some of these fainter objects, we were also able to recover as either kind of marginal signals, or this one was not so well recovered, which is partly because it's really faint and partly because it's only at about 30 AU from the sun. So you start getting nonlinear motion from the object. So something I should mention is this survey that we're doing is truly just looking along linear paths, with the idea being that outer solar system objects are effectively static relative to Earth and also the TESS spacecraft. And so as Earth is moving past them, it looks like they're moving effectively in a line that's just following the parallactic motion of the Earth. So that's what we're looking for. It works well for distant objects, but paradoxically is actually worse at finding nearby objects. So good for finding distant, bright bodies that are not moving very much on their orbits. So Within this 2021 paper, Brown and Batigan suggested a specific location that they think is really likely for Planet 9 to be in the sky if it exists. So we said, okay, well, TESS has observed that entire area effectively, and so we'll just go out and see if we can dig up anything interesting from the test sectors that are located there.
Before you go
Yeah.
on, are you finding objects, record objects with record submajor axes in the Orbital?
Yeah, so that's part of the goal. I'll talk about this a little bit later. The main issue. Yeah, so we're looking for anything bright that's moving at the right rates. So we're considering anything effectively beyond the Kuiper belt. So,
okay, so
yeah.
it's a bit of a matter of definition. I know that there's a short period comments and so on.
Mhm.
The other question was, do you get into a situation where it's moving slowly enough that you don't actually are able to measure some major axes?
If it's moving too slowly, then it's hard to distinguish from a star. That's the main issue that you get. Because when you shift and stack and it's only 2 pixels, then it might just look like jitter from the spacecraft.
So you get the parallax.
Yes, so you don't get much or any orbital information from this because you're just doing a linear shift stack. So you just get the distance, and if it's far enough, then it doesn't move very much year to year, and you can just follow up with other ground-based telescopes to get the orbits. But really, you're just getting a position at a time, and if it's very far, it won't have moved far from that location, so you can follow up.
So what is the upper limit on the radius we can detect over tests over 1 AU's worth of parallax?
Do you mean the orbital separation?
Well, you're seeing it move because of the Earth moving back and forth.
Yeah.
So how far out can you actually distinguish? In other words, what's 1 pixel's worth and what distance is 1?
1 pixel is 21 arc seconds. So Planet 9, if it was at 800 AU, would move about 5 pixels in 27 days. So it's still observable, but if you're thinking thousands of AU, you're not going to see anything.
Exactly. That was sort of like Christmas point.
But even 5 pixels is a little marginal because some of your stars are pretty bright and then they saturate the regions around them as well.
I'm sorry, just before we move on, do you want to maybe move the
Oh yeah.
Zoom?
Can't see my mouse, so it's kind of hard to.
Okay. Well,
Well, you might have to turn up the stop sharing.
there we go. Okay.
Oh, there. And then can you hit the turn up volume?
Turn up volume. Oh, yeah.
Can't see the mouse, that might be hard.
Challenging.
Yeah.
What if I just fix it and I go back in?
Yeah, there you go. And then you can do this.
Okay.
It's all my notes. Okay. So this is just showing some of our known object recoveries that we've had. So these are blind detections, but they end up coming out of the shift stacks. There are a bunch of known objects that come out. We have a whole slew of new candidates that we've just been working through vetting. So some of this vetting is on Sky, but honestly, I think there's a lot more computational vetting that we can do to just check, if you split your sector into 2 halves, you get the same kind of marginal discovery in both halves. If you shift stack backwards and forwards, you get the same signal. So if you didn't mask a star properly, then you might expect to get the same signal, but if it's a slow-moving solar system object, you wouldn't. So these are some of the tests that we've been running through to just try to reduce our candidate list. We only had about 20 strong Planet 9 candidates. This is actually one of them. This one was my favorite one because it shows this nice little sync function that we're seeing for a lot of the real objects, where you end up, when you have an actual bright object and you're discretizing it into individual pixels, this is something you also see in direct imaging. You end up recovering it once you do the shift stacking with a little sync function profile that's related to taking a Fourier transform of a top hat function. So we ended up seeing that here, which looked pretty promising. We haven't recovered it on Sky, but we've had somewhat cloudy days, so I'm not 100% convinced that this guy is not Planet 9. But if it's not, then I don't know, we might not see it within that region. It's kind of where we stand right now. We're not just looking for Planet 9 though, we're also looking for anything else that's in the distant solar system. So Ben Cassess, who is co-advised by me and David Kipping at Columbia, is doing a lot of great work to actually do this follow-up and check which of these objects are most likely to be real. And he recently discovered our first confirmed TNO, which is a pretty normal TNO. It's at 35 AU on a circular orbit, probably. We don't get much orbital information from this follow-up, but this was our first very clear blind detection where we went on sky and we were able to follow it up just a couple months ago.
Do you have a size for it, estimate or not?
I do, but I don't remember off the top of my head. So, but it was fairly bright. It was, I think, V equals 21.8 or something, so not incredibly faint.
But not known previously.
Not known previously, yeah. So in general, we're trying to make this just a fully functioning pipeline that every time TESS has a new sector of data, it's going to process it, come up with any interesting candidates, and then just put them out there for anybody to follow up. So we're really just at a point where this pipeline effectively exists and we're just doing robustness testing because we don't want to give thousands of candidates where most of them are most likely not real. So that's this pipeline that we're putting together that's really being led by Ben, but we have some fantastic collaborators at the CCA, CITA, Harvard, and MIT that are also helping out with getting this up and running for upcoming test sectors. So hopefully there should be a lot more of these great solar system objects detected. Right now there are pipelines to pull out the objects that show up in individual test images. So if you can see the point source in individual test images, you can just connect the dots. But there's nothing that is able to go below the single frame detection limit yet. So that's something that we're working on. I also wanted to mention we keep accidentally finding stuff. So we accidentally found Uranus and Neptune. And actually all the solar system planets will have been observed by TESS within about a year or two. So I have a couple of undergrads who are going to be taking a look at the light curves because these are continuous light curves of Uranus and Neptune for about a month. And we're starting to get those for lots of objects in the solar system where you can start trying to understand more about atmospheric variability, which will be a fun new foray for me. All right, so that's Planet 9. We'll next go to interstellar objects. These are just kind of my fun intros before I go into like my extensive exoplanets stuff. But I briefly had a little stint looking at interstellar objects because they were discovered during my PhD. And so this is something a lot of people are really excited about. And I particularly think they could be a pretty useful avenue to learn more about extrasolar planetary systems in a much more detailed way than has been possible, and that likely will be possible in the upcoming years, at least from a direct chemistry perspective. So the first two interstellar objects, these are objects that originated from outside the solar system, probably some kind of asteroid comet-like thing, passed through and left. They're not bound. They were first found, the first one was 2017, one Oumuamua, and a second one, Borisov, was found in 2019. And there have been none found since, which is kind of unclear whether that was heavily impacted by the pandemic or maybe they're just not actually all that common. But it's been about 5 years since we found Borisov, and there's still ongoing searches to see what else we'll find. So it was surprising that we found these two objects because they're quite large, and there have been previous predictions that interstellar objects exist and they're just rocks floating around, but it was expected that the size-frequency distribution would be kind of out of our favor for actually observing these anytime in the immediate future, and that there would be many, many small bodies that we would not be able to see, and not objects that are hundreds of meters in size that would actually be detectable and likely to pass through the solar system in these short time scales of our observations. So this kind of poses an issue if you think these come from planetary systems, or sort of poses an issue in that most of our known exoplanets are pretty bad at efficiently ejecting planetesimals. So our known planets tend to be biased towards very short period orbits. And that means that this Safronov number, the escape velocity squared over the orbital velocity squared, ends up being quite small for most of them, and it's quite difficult to eject material from these planets. So these planets are not good at providing the gravitational lift needed to actually toss things out of the system, the way that Jupiter in our solar system is fantastic at tossing things out. So there is sort of a rough location at which a given planet is relatively good at tossing things out. So if you take this function and you just say the mass and the radius are roughly proportional to each other, then for a given stellar mass, there's a semi-major axis at which planets are pretty good at tossing material outwards, which tends to be at least 1 AU. It helps to have more distant, wide-orbiting planets to actually eject planetesimals. Around this time, there was this beautiful gallery that was released by the D-Sharp team of protoplanetary disks that suggested there may be planets or something else that's producing axisymmetric structures in a pretty huge number, a pretty huge fraction of our protoplanetary disks. And generally, as higher and higher resolution images have been taken, even the ones that look featureless, some sort of feature tends to pop up if you just keep imaging at better resolution. So if these were actually carved out by planets, which is still very much up in the air whether that is the case, then Zhang et al. 2018 suggested from hydrodynamic simulations that they would roughly fall within this range of parameter space where we haven't really seen many planets at all yet. So these would be a completely different kind of planet that kind of borders what we see in the solar system, but that we're not really seeing in exoplanet systems in any direct way. So this is kind of the most, it's an indirect piece of evidence that maybe they could exist.
So,
Yeah.
in other parts of the element disks, you get the right astronomy, you don't need much mass.
Sorry, can you repeat
In
that?
other parts of the element disks, in order to get a big enough astronomy, you don't need much mass.
A small planet can eject
Yes.
these bonds.
Yeah,
I mean, a smaller planet that might be an imprint disk, actually. You're talking about quite large stuff, something there.
Yeah,
And so I couldn't
Yeah.
see this, the scale on the
Yeah,
plot
sorry,
you were
it's-
showing,
it's this that you're referring to.
Exactly.
Yeah, so if you are at a wide orbit, then smaller planets would also be more efficient.
So I'm sorry, the next plot that you were just putting back on.
This one?
Yeah, so that was on a 10 to 2, or I can't see. Sorry.
Yeah, 10 to the 3 is this last
10 to
tick.
3,
10 to the
okay.
3, 10 to the 2.
Yeah.
Yes. So,
So there is a possibility of some, completely so far undetected population of minor bodies that could be scattering each other out.
sorry, are you referring to planets or minor planets?
Well, just referring to the interstellar objects.
Yeah.
Relatively minor planets that. Well, I guess, okay, sorry to let down a little bit, but
That's
the first
okay.
part you were talking, you were
Yeah.
describing constraints on objects out to about 1,000 AU, right?
Yes, but they have to be quite large to find them at that distance.
So there's a simple question is, what's the upper bound on the size of the object that you can detect? Relative to the size of the objects that could be scattering out other objects at large radius. Because, are you directly sensitive to them, or would they be falling under the radar?
So you're referring to interstellar objects
Yeah,
in the outer solar
So-
system?
So, could our solar system have objects that we're not yet sensitive to out of 100,000 AU?
Yes. Yeah, so
that
they're,
we're still big enough to be creating, by gravitational interaction, some population of interstellar objects.
I see. So are you saying, could the solar system have planets in the very distant regions that would be good at?
If you want to call them
Producing.
planets.
Yeah. Yeah, so that is possible. That goes back to this map of, you can see exactly how much space remains here, but you could have lots of different kinds of planets, but here the semi-major axis scale is 10 to the 2 to 10 to the 3 here. So if there was anything there, then it would also be probably pretty good at efficiently ejecting things. But I would say in our solar system, we don't actually need to invoke that to say we tossed out a lot of mass interstellar object material, and that's just because we have a Jupiter. But I mentioned earlier that the Jupiters are also only found around about 10% of sun-like stars. So while that works for the solar system, it doesn't necessarily work for all planetary systems.
But I also would say the Sakharov number is not the only number that matters in terms of tossing things out. The timescale goes very long for low mass travel.
Great. Yeah, so we didn't consider lower mass planets here, but that's a good point that your timescales will start to play a larger role if you're considering smaller and smaller planets. Okay, so the punchline here was really just that if there are Neptune-sized planets here, then they would be very good at ejecting a lot of interstellar objects. So if we do find a lot of interstellar objects, then that might mean we expect wide-orbiting Neptunes to possibly be more prevalent. That's not to say that's the only way that you could produce this underlying population, but it's one way. And if you did expect that these interstellar objects were ejected by Neptune-like bodies, then you can extrapolate with just assuming a power law size frequency distribution of interstellar objects that are free-floating, that we should see probably something like 1 to a few interstellar objects of Oumuamua size each year with LSST, or the Vera Rubin Observatory. But if we're able to start seeing some of these smaller and smaller objects, depending on the exact survey strategy of how often you're returning to these points, and whether you're able to detect these smaller, fainter objects as well quite efficiently, then we might expect to see quite a few interstellar objects. So this is still very much up in the air, I would say, just how many we are going to see with LSST, and hopefully that will be a good high number. That would be quite interesting for actually studying material from extrasolar systems. But this is just one possible avenue that you could produce that very large underlying population of quite large planetesimals as well. Okay, so I want to move on to exoplanets for the rest of the talk. I've been doing a lot of work on exoplanets, especially over the past couple of years, trying to understand the mechanisms that produce the diversity of exoplanet systems specifically. And a lot of my work has been I've been approaching this problem using these measurements of this concept of stellar obliquities. So this is just this angle between our stellar spin axis and your net orbital angular momentum vector is the stellar obliquity. What we actually generally measure is a sky-projected version of this for individual exoplanets. So we end up being able to see which way an individual exoplanet goes relative to the stellar spin, but the stellar obliquity, you'll see in the literature, is the term that's often used. I would say we don't know the stellar obliquity for any exoplanet systems because we don't know where all the exoplanets are, but you'll see the term used pretty often. So I just wanted to mention that it's kind of the same idea that I'll be talking about. So the solar system, we do know the obliquity because we know where the planets are, minus maybe planet 9. And the solar system is slightly tilted. So the planets are in roughly the same orbital plane, but tilted by about 6 or 7 degrees. In exoplanet systems, lots of transiting gas giants have had spin-orbit orientation measurements made, and many of them are misaligned. Not all of them, but lots of them are orbiting sideways or backwards on these crazy orbits relative to the way their host star is spinning. So I made this figure 2 years ago, and I had this dream of all the things that I'm going to do. And so I'll talk about the progress I've made towards this dream over the past couple of years. But there are a lot of things that we can do to try to understand how the initial conditions of exoplanet evolution look based on these spin-orbit orientations. So what kinds of systems do or do not get perturbed onto these misaligned orbits. And we can figure out whether this is or isn't related to eccentricity excitation. whether small planet systems are also heavily misaligned very often. There's a lot that can be done that is starting to get done because we're getting increasingly precise, high precision radial velocity observations that can be made with these kind of like 10 to 30 centimeter per second precision instruments that are very new as of just the past couple of years. So to actually measure these spin orbit orientations, which I mentioned, we're just getting sky projections usually, we use something called the Rosser-McLaughlin effect. So the idea here is if you have a transiting exoplanet, as it passes over your star, it's going to cover up different parts of your star, which is also spinning. So it's got a blue shifted and a red shifted side. And depending on what part you're covering up, you're going to produce what looks like a tiny shift in the net radial velocity from your star. So what that ends up looking like is for an aligned system, you got something like the bottom left here where it's nice and symmetric. You cover up the blue and the red parts the same amount of time. And if it's not aligned, then you end up with some kind of asymmetry where you either get kind of one side of this bump is much larger than the other, or you could just get a fully one-sided deviation here. The amplitude of this effect that we expect is a very strong function of transit depth, as well as their projected stellar rotational velocity. And so what that means is we're pretty good at finding or getting these observations for cross-rotating stars as well as giant planets. So I'd say this is probably the most kind of important constraint where it's good to keep in mind almost all these observations to date have been for giant planets, and that'll be what I'm talking about for the rest of this talk. So there was this discovery in 2010 that it looks like hot Jupiters around hot stars are more often misaligned than hot Jupiters around cool stars. This is Wynn et al. And Schlafman in 2010 showed that with a pretty small sample size, they're seeing that there are quite a few misaligned systems on this side of this line here, and fewer on the left side. So I want to just start by drawing your eye to what this figure is showing. So this is, again, a proxy for the actual alignment, because this is just the sky projection, but kind of roughly you can think the ones at the bottom of the figure are aligned. The ones in the middle are polar-ish. They could be kind of arranged near polar, but kind of roughly you can think of them this way. And then the retrograde ones are going to be towards the top of this figure, keeping in mind this is a 2D angle, not the full 3D one. So this is the trend that was pointed out, and the reason that Wynn et al. Put forward for why this might be the case is that above the craft break, your stars have a radiative envelope and they're not very good at dissipating energy. So they're not good at realigning to the orbit. Whereas below the craft break, your stars have an outer convective envelope and might be able to realign at least a portion of the star, if not the entire star, to your misaligned orbit. So this is the time scale that it takes for that obliquity damping to occur. And around both of these stellar types, this mechanism would occur, but depending on the mass of your convective zone on the outer part of your star, you may or may not be able to do this in observable amounts of time or within the age of the universe. So this is something that's held for quite a long time. So the previous figure maybe looked a little less immediately obvious that this is convincing, but 14 years later, more and more observations have been taken, and this holds up pretty well. We're seeing a lot of misaligned hot Jupiters kind of all over the map around hot stars, and around cool stars, there are very few that are misaligned. So there are quite a few ways that you can make misaligned hot Jupiters. I'm going to just categorize them into three possible mechanisms that tie very closely into this question of how do you get hot Jupiters in the first place? These are very, very massive planets, very, very close to the star. They are kind of difficult to form in situ because there just isn't much material in the inner part of your disk. So if you want to form a misaligned hot Jupiter, you could form it somewhere within this disk. It could either migrate or somehow form in situ. And if your disk is tilted in the first place, you could just form a misaligned planet that way. You could have some sort of planet-planet interactions combined with high eccentricity migration, where generally you eject one planet or more from the system, and another ends up on a very eccentric orbit that tidally circularizes to get your ultimately usually circular orbit for a hot Jupiter. Or you can also have some kind of star-planet interactions, which could be something like a flyby, or could be something like Kozai-Leadoff interactions on secular timescales. I should note, planet-planet interactions, there's kind of a wide variety of flavors of that as well. So I'll categorize these as basically two scenarios that we're trying to distinguish between, which is either your hot Jupiters form in a nice disk and they never undergo any dramatic evolution, or they undergo some kind of dynamically violent evolution mechanism. That's the right two panels from the previous slide. So if we expected this dynamically violent mechanism to occur, then there should be some relationship between the misaligned planets and eccentricity. So just as a reminder, here you need to have a high eccentricity at some point to circularize to your short period orbit. But if you somehow formed a hot Jupiter quiescently, then there's no reason you would ever have to excite your eccentricity. You could just stay on a nice circular orbit for the entire formation of your planet. So we said, okay, we'll add another dimension to this. This is a somewhat complicated figure, but I'll walk through it. So here we're looking at how, as you add together lambda values, these are the spin orbit misalignments, it compares when you look at just eccentric orbits. So the hot Jupiters on eccentric orbits are in purple here, versus the hot Jupiters on circular orbits are in gray. So there are many, many more hot Jupiters on circular orbits, which means that we just take a random set of 21 here, for example, and just figure out what the cumulative sums look like for many random draws of 21 hot Jupiters on circular orbits, and compare them with the eccentric hot Jupiters to figure out, do we end up with many more misaligned eccentric hot Jupiters? And it looks like we do. The main thing here in this cutout is just saying that you end up with a pretty large difference at the Kraft break, where many of the eccentric planets are misaligned even around cool stars below the Kraft break here, whereas you don't see that for the circular orbits. I think another way that this might be a little bit clearer to understand is if you just take the full distribution of hot Jupiters on circular orbits equals 0 versus eccentric is greater than or equal to 0.1, split them into above and below the Kraft break. All these lines match up really nicely with each other and are pretty much consistent with the same line except the purple one. So what we're finding is that hot Jupiters on circular orbits around cool stars tend to be aligned, and all the rest of them have kind of a broad range of misalignments. So they don't have a very strong peak towards 0. It's only the ones that are around cool stars and on circular orbits that are really, they tend to be aligned. All the rest of them are all over the place here. So just to reiterate again exactly what I'm saying here, this was the initial finding from 2010. Hot Jupiters usually aligned around cool stars, often misaligned around hot stars. And what we found is that if you add this extra axis, it's really just this one quadrant that is actually often aligned. The rest of them, hot Jupiters tend to just be misaligned around if they're either eccentric or if they're around high mass stars. Or there's no evidence that they're more aligned than other systems. So all these lines also match up pretty nicely with expectations from various mechanisms that are often invoked as starting points for high eccentricity migration, which is this dynamically violent hot Jupiter mechanism, or formation mechanism. So what we proposed in this paper is that hot Jupiters are, as a population, very well reproduced by high E migration. And this purple line would just then reproduce the planets that are the most evolved. So all of these planets are moving towards circular and aligned orbits over some time scale that you can quantify with the obliquity damping time scale. And I didn't put it here, but there's also an eccentricity evolution time scale. If you just take a very simple, this is just equilibrium tides, we're not thinking about inertial waves or anything else, although I'll note that Zanazi, Chang, and Dewberry treats this much more in depth and actually does a really good job of also showing how you can reproduce the joint eccentricity. distribution. Yeah, but even with a very simple model, you're able to pretty well reproduce the purple distribution, which I should note is not like the most robust in that there are only 5 planets that make up this tail beyond 35 degrees. And so it's a pretty small sample that's defining like this entire part of this distribution. So I would say that this agreement is actually fairly decent given the sample size. And I also don't expect equilibrium tides to work perfectly here. It was truly meant to be a first order approximation of can you create hot Jupiters by just saying all of them form through something related to high migration, or most of them, and then also applying tides to.
So on that point, can you go back one more slide with your 4 squares? So the blue one, they usually align, what fraction of the hot Jupiters is that?
So that is, let's go back to, so the purple I mentioned, beyond here there are only 5 planets. So if we say 35 degrees, it's kind of generous to say misaligned, is misaligned and the rest are aligned, that would be 27 that are aligned. So
And they're below the craft rate.
yes, all of those are below the craft rate. Yeah. Okay. All right, keep moving. So that, just in summary, kind of points us towards dynamically violent hot Jupiter formation as a viable mechanism to produce all these hot Jupiters. So that's not to say it's the only one, but it does a pretty good job of producing the full distribution for both eccentricities and spin orbit orientations. Another way you can approach this is looking at warm Jupiters, because warm Jupiters, despite being on just slightly wider orbits, usually defined as greater than 10-day orbits. I define it by A over R star here because I'm concerned about whether these systems will tidally realign or not. And so I want them to be at a wide orbit where they're difficult for the star to realign. So the warm Jupiters, despite being on just slightly wider orbits, have a lot of companions, and they probably can't form through high migration. And so they seem to have fairly different properties from the hot Jupiters, even though they're not so different really, they're just slightly farther from the star. So we've been getting a bunch of spin orbit measurements for these because we just want to figure out, if you don't have the degeneracy of they might have been tidally realigned, what does this distribution look like? So this has been an initiative with Songhu Wang and Shunyu Wang at Indiana University, the Stellar Obliquities and Long Period Exoplanet Systems Survey for SOLS that I started during my PhD and have been continuing. The main motivation was, if you just look at this set of spin orbit orientations split up as below the craft break, above the craft break by orbital period, I made a lot of plots and just was trying to figure out what this distribution actually meant. I noticed that the hot stars on wide orbits, or all the Jovian planets that were orbiting hot stars on relatively wide orbits, were not misaligned. And that seems strange, given that we noticed all these hot Jupiters that were misaligned on shorter orbital periods, and we're not seeing it at the wider orbital periods. But this is a really small sample. So I said, okay, we're gonna go out and we're gonna expand this. We have, at this point, gotten 19 measurements, so I've run out of space to add more, but this is just showing the first 10 of them. And we have quite a few more that are along the way. These stars are undergrad-led papers, so very proud to have some of the undergrads getting some experience with the research process through this program. And I want to point out a few of these are by students who have worked directly with me. So we have quite a few results that are either published or on the way, and I'll talk through some of these in the next couple minutes. So the first thing is that it does look like the warm Jupiters, as long as there's not a stellar companion in the system, are pretty much all aligned. So these are these pinkish points here, and we're seeing lots of hot Jupiters spin orbit misaligned on the left, so those are purple. But if you look at these pink points that are at wider star-planet separation, they're all aligned. And that doesn't actually apply to the Saturn mass planets. So if you look at lower mass planets, which might be a bit easier to dynamically excite if there are other planets within those systems, they don't all end up being aligned if you look at the very low mass end of this range. So this is just a very simple test of just saying, okay, well, we've seen 12, we saw 0 misaligned warm Jupiters, and if we just take random draws from the hot Jupiter population, how many times do you end up with actually just 0 misaligned systems? And so this was about 3 sigma at the point that we had published this. More recently, an undergrad student working with me worked on another measurement that was a hot Jupiter, or a warm Jupiter around a hot star, and kind of further filled in a bit more of this space, also with other archival measurements that have been made recently. And something particularly interesting here is that what's increasingly found is that even the warm Jupiters on really eccentric orbits are still really closely spin orbit aligned. So it seems like they can get to kind of high eccentricities without ending up misaligned with their host stars, whereas the hot Jupiters still, they get excited in eccentricity and or spin orbit alignment, and we're not seeing that for the warm Jupiters. There was a question of whether this applies for both hot and cool stars. So this is actually work in prep, but we recently got another 6 measurements of spin orbit angles for warm Jupiters around hot stars, and they're all aligned. So we're finding lots and lots of aligned warm Jupiters, and it looks like whatever mechanism is misaligning the hot Jupiters is not working for the warm Jupiters. It's a different population, or it's a tail of a population that somehow does not get spin orbit misaligned in its evolution. So that, to me, really is pointing towards hot Jupiters forming in some dynamically violent way that is not applying to the warm Jupiters. That's why they don't get spin orbit misaligned. They still keep their companions, and they tend to have other planets within the system, which is not so common for the hot Jupiters.
So that warm Jupiter you pointed out had eccentricity 0.8.
Yeah.
Isn't that going to become a hot Jupiter at some point?
It might. I would have to check what its paracenter distance is. Because I don't.
1 minus e is 1.8.
0.2 times
Yeah.
20.
4.
Yeah.
Yeah.
Become a hot Jupiter. And
So, yeah, so Cristobal Petrovich suggested this idea of coplanar high E migration. So it might be that it will migrate in a coplanar way. And for some reason, the rest of the hot Jupiters are not doing that.
Well, it'll stay coplanar if it is.
Yeah.
But the question is how to get such a high E without producing any I. Scattering won't do that.
Yeah, that I would say remains not fully solved. And there have been quite a few unpublished measurements of eccentric warm Jupiters beyond these ones that also seem to be showing the same thing. So I think Cristobal Petrovich has some ideas on this, but I think they are related to some kind of like planet-planet scattering secular mechanism, but
Without
Yeah.
changing the inclination.
yeah, it's challenging, yeah. So the warm Jupiters have been quite interesting.
Yeah,
Are these also single planet systems? They're not multi-planet systems? The warm Jupiter typically?
Some of these do have companions.
But these
some-
tiny ones probably don't, I guess.
Yeah, I don't know if 3362 does. I'd have
not
to check.
in factor 2 and 7 major axes.
And I'll emphasize that this is just single star systems. If you have another star in the system, that totally messes it up, and you get misaligned warm Jupiters. So
That's not messing it up. That's what you'd expect.
yeah, it's what you'd expect. Okay, I could probably skip this because I want to get to this last section that's looking at binaries, because I accidentally got really interested in binaries because of this one specific measurement of Qatar 6AB, which is a normal aligned warm Jupiter. It looked super normal, but it had a stellar companion. So I said, okay, what's going on with the stellar companion? And let's just do a thorough job of understanding the system. And if you just look at the position vector between the two stars in the system and the relative proper motion vector, it's only consistent with very perfectly aligned orbits within 1 degree. And we know that our exoplanet is also aligned because every single one of these measurements is for a transiting exoplanet, so they're all edge on. So it looks like this system is both spin orbit and orbit aligned. So that seemed weird. It was very precisely aligned as well. So I said, okay, well, how normal is this? If we look at all of the systems with spin orbit measurements and just figure out the binary orientations, what do they look like? And this is just why you might not expect them to all be aligned, basically the Kozai-Ledoff mechanism. So around this time, there was also a set of observations by Christian et al. 2022 and Dupuy et al. 2022 that basically said if you find transiting exoplanets in wide binary systems, so your exoplanet's around one star and there's another stellar companion, and you just figure out what the distribution of the binary inclinations is, there's a peak towards edge on. So that means that your binary systems tend to be nicely aligned, orbit aligned with your transiting exoplanet, which is also edge on, at least in this 1D inclination direction. And this was done for the TESS TOI sample, as well as Dupuy et al. Did something very similar around the same time with the Kepler sample using astrometry. They found similarly, even at quite wide orbits, so these are stars out to about 700 AU in each of these samples, they're finding this tendency towards orbit alignment. So this is just a map of the various configurations you could have, a couple of the well-constrained values for spin orbit and orbit configurations. So if you wanted to look at both of these together and figure out, this is what Qatar 6 looks like, jointly spin orbit and orbit aligned, but you could have all these other orientations. We went ahead and just said, okay, what does the distribution look like for all the systems where we have each of these measurements? And so I've mentioned the spin orbit angle a lot so far, but I want to just emphasize the definition of this orbit angle is the position vector between the two stars and the relative velocity vector are the two lines that define that angle. And it is quite well defined for aligned orbits, but if your orbit is misaligned, then there's a degeneracy between how misaligned it is in inclination versus eccentricity. So it's kind of hard to tell how misaligned it is, but you can tell whether it's consistent with edge on. So this is just showing that set of all of these systems. These are pretty biased towards hot Jupiters because they all require spin orbit measurements to be included in my sample. So we have mostly giant planets that span this pretty wide range of both gamma and lambda values, and I use some isochrones fitting to also translate to inclinations, since that's a little easier to think about for some people. And a couple things that came out of this, we found no clear correlation between spin orbit and orbit misalignments. There are points kind of all over the place. But we do see an overdensity of spin orbit and orbit aligned systems. So everything is super nicely aligned in these systems. That's the 9 systems that are shown here. So as a reminder, when you have an isotropic distribution, you actually expect most inclinations to peak towards edge on. So isotropy actually does peak towards edge on, but we find even more edge on than you would expect from isotropy. So this is just showing what that sample looks like and kind of what we use to set that. It has to be pretty stringent and low uncertainties, relatively speaking, for each of these measurements. And we find this kind of marginal deviation from just small sample size uncertainties when we look at our full sample. But our full sample has some issues with it in that it includes very wide binaries, and it also doesn't differentiate between different stellar types. So returning to this figure that I showed before, something that I've been thinking about more and that might be a useful clue to what's causing this is that we see this really strong peak for our cool systems, cool star systems, so low mass stars for both the host star and the companion star tends to be lower mass. But when we look at the hot star systems, we're not really seeing anything. And it looks to me like the hot star systems are perhaps just more often undergoing these Bonsai-Ledoff Kozai oscillations that are producing these double peaks away from 90 degrees. So there have been a couple studies showing what we might expect this distribution to look like. Fabrici and Tremaine 2007 had this beautiful result that doesn't include the octopole potential. So Mausethal 2012 does include the octuple potential, and the exact signature that you'd expect depends on binary separation and various other things. That's why we have different colors here. But each of these distributions basically just has a dearth of 90 degrees edge-on systems. And so that's what we seem to be seeing for our hot star systems. So what we think is happening is this viscous dissipation idea, which is effectively when you have a companion star and you have a protoplanetary disk, it's going to cause your disk to recess, or so nodally recess, and your disk is going to dissipate energy and get closer to this edge-on orientation. This is not the most efficient for wide binaries, so this works very well for very close-in binaries. But if you're starting to look at wide binaries, your disk either needs to be quite large, so you want this damping rate to be fast. You want either very big disks or very high viscosity or something that usually actually requires you to have not the most physical disk parameters for 700 AU separations. So it's still a bit of a mystery exactly whether this is the only mechanism that's causing this orbit-orbit alignment or whether there are some others at play that are working here. So I wanted to mention Konstantin Gerbig is a PhD student at Yale who has been working on the theoretical underpinnings of this mechanism and trying to see whether it's going to actually work even out to these wide separations. So this is just an example of a suite of runs that he did for just setting a range of disk binary orientations, the spin of the star versus the disk orientations, and trying to figure out what the outputs look like to match both the lambda and the gamma distributions. And one of the main takeaways that we got from this is that if you do have this viscous dissipation working efficiently, then you should expect it to be far more efficient if your companion star is more massive than your primary. So the more massive your companion is, the more efficiently it's going to enable your primary star to dissipate energy and get closer to that orbit plane. So that's kind of what this is ultimately showing, primarily these top panels, but we also show the expected spin orbit distribution below as well, which also actually matches quite well with current observations. And it looks like we actually are seeing that in the data. So we find that if you look at just where the primary star is very low mass, this is a pretty small sample, so it's kind of hard to tell, but there isn't, if you have, I guess, either equal mass or your primary star is lower mass than your secondary, then you end up with the inclinations being a little bit more peaked in this direction. Then here you see absolutely nothing. So this is just effectively consistent with isotropic. So it looks like it might be playing some important role, but maybe isn't the only mechanism. So I'm just going to skip past this because I think I'm out of time, and just say that it looks like both of these are probably playing quite an important role in setting our 3D geometries for our binary star planet systems, and just how much of a role each of these plays for different stellar types and different separations is still kind of being observationally worked out a little bit more. But it looks like both of these are probably prevalent, and this one on the left is definitely not talked about as much, at least among observers, and so hopefully it will be more soon. Okay, so that's all for my talk today. Just stepping back, really the goal of all of this is to try to understand planetary systems in general, trying to understand our solar system in a broader context. And so I'll just leave with some very general conclusions and take any questions.
Very much. Do you have any questions?
Thanks. This was really fun. I'm not sure if I just missed this, but like at the end you were talking about like the hot Jupiters around like binaries and tertiary three-stars. But then earlier you were showing like a plot. I think it was when you were talking about like the circular hot Jupiters, and you had it split into like blue and red for like cool and stars, but then like some of them you outlined, and you said that the outline meant it was like a binary star, right?
Yeah.
But you didn't have a lot of outlines. You had more single stars. So I'm wondering if that means that you get these hot Jupiters more frequently with, single stars, even though I thought they were more binary stars in the world. Universe.
Yeah, that's a good question. A lot of hot Jupiters have been found in binary systems, but they are often more difficult to follow up with radial velocity observations. And specifically, if you want to get these Rossner-McLaughlin observations, you need to be able to separately resolve the two stars. So if your binaries are too close, then you can't get these measurements. So I think that's probably more of a follow-up observation bias than an underlying system property. There are also hot Jupiters around single stars, but there are a lot of them around binary or in binary systems as well. But yeah, for reference, the binary sample that I was looking at was about 40 systems. So it's mostly hot Jupiters, but there have been something like 200 spin orbit measurements made, where I'd say probably 170 would be hot Jupiters. And I think that's just bias of it's easier to get radial velocity follow-up for single star systems.
Okay, that makes sense. Thanks.
I have a question about this disk alignment work. You talked about that there's an observational difference between the hot and cool stars, and then in the theory there's this difference you get for different mass ratios. Does the theory looked at make any predictions for a temperature dependence as well?
Yeah, so it's a good question. Trying to think about how to best answer that, because the mass of your primary star versus your secondary star should definitely matter because of this mass ratio effect. And I guess the hotter stars, it may just be that they either dissipate more quickly or they might end up emerging in high mass systems with like multiple planets or something that ends up preventing the viscous dissipation from occurring quickly. I would say this is not something that I have a full answer to exactly, but I think we're seeing potentially the hotter star systems are more often undergoing ZLK, but there's also this slight bias where it's in a figure that I didn't get to show. The hot stars also tend to be at slightly wider separations. So we are seeing some misaligned ones that are at close separations, but because the binary separation distribution isn't the same, it's a little hard to say for sure that this doesn't ever happen for the hot star systems, or if it's specific to hot Jupiters or something.
And then, sorry, just how are you defining the temperature for the binary? It's some average between them?
Just looking at the primary star, and then the secondary star is almost always lower mass. So, yeah. Just the punchline here had been that if you just look at the smaller separation systems, you actually see a stronger peak towards this alignment, which is what you'd expect for viscous dissipation, because it should have basically no effect beyond 2000 AU, which is already pretty optimistic.
Okay, well, if maybe we can continue discussion over cookies and cocktails. So let's thank our speaker once again. Centric warp Jupiter. Yes, those Mars.
Secondary eccentricity only, right?
So when it
That's great.
is, that's not
Yeah, but then you also have not have any nearby.
you want the second.
I was also wondering, so-
Secular pairs. And then
Very
you want
intrigued.
this, which is specific.
Sorry.
I was very intrigued by test observations of solar systems. Are you
When there was
are
one
you looking at all of the
system
backlinks there?
There's a companion.
Yeah, so Uranus and Neptune, I have some students lined up to look at, but Jupiter and Saturn, I think we don't have observations
So that
yet.
would be one
We'll
thing.
get
That
that
sounds like a good
insight.
Yeah.
Yeah.
In fact, that could also
So we should actually have most of the solar system planets, if not all, quite